Thank you, Mr. Lee, and thank you, Mr. Dersh, for providing me with this opportunity. I really want to take this moment to show my appreciation to the Department of Mathematics, who I consider myself as a product, and I'm proud to be part of the history here at GICC. So to be starting off, my presentation, you guys, Mr. Lee has already mentioned about a little bit of my background and where I'm coming from and things of that nature. So how do I move to the next one? Okay. So just going a little bit over the agenda today that I want to hit up those main points. I consider this as a warm-up period. Next one is going to go through some main components of mathematics in the industrial engineering. Third one, consider it as a main body of this presentation to be LP, or linear programming, forecasting methods, and then wrap up with some questions and answers. So I want to start with the questions that I want to pose today. What does it mean to be an engineer or to be an applied mathematician, and when are you becoming one? So I wanted you guys to keep in mind that question during the presentations. I want you guys to work with me as far as if you have any question, any concern. I want you guys to interact with me, ask me a question anytime, stop me anytime you want to. So I want you guys to keep in mind with these questions and moving along as the presentation proceeds, right? So to me, after a couple of internships in my second years and up until my senior years, I realized and asked myself, what is really an engineer and who is an engineer? So to me, a career of an engineer is applied math and politics and some buffer, okay? So not always 100%, but also those are the two main components. So the career index is obviously the weighted average, right? So industry experience and degree market, okay? But degree market depreciates. Here's how. What do you think a 4-year degree in engineering is worth the same as a 4th-year degree in engineering 20 years ago? If you ask yourself that questions, it really comes in and triggering my mind that in the span of 20 years, the amount of technologies and new software and things like that being integrated into the programs and into what we've learned and into part of our academic life, that makes our degree values depreciate. Not a lot, but it does. Industry experience, on the other hand, does not. It means that the more year you are in the industry, you will be able to accumulate more experience, and that experience won't decrease in values, right? So when are you becoming one? So after you graduate, you will have an FE certification, right? Fundamental engineering. You have to go through a 6 to 7 hours exams. After a period of about 4 to 5 years, you reach your PE certifications, means you have to sit into another exam. Obviously, more challenging than an FE, right? So today, I want to talk about this portion of being an engineer, the applied math, the mathematics in the world of industrial engineering. So, applied math. To me, there's other stuff that factor into engineering nowadays, but to me, there's two main components called operation research and statistics, at least under the eye of an industrial engineer, okay? So, as an industrial engineer, we are facing a couple, just to name it here at least, right, of these problems that we've seen in the future in our job. Cost or resource minimizations, engineering planning, risk management, human resource scheduling, routing, capacity planning, project management, LP problems, line balancing, logistics and all that, flight scheduling, forecasting and stuff like that. So my question to you guys is, what are the common things about these problems, right? What do these problems has in common that industrial engineer has to solve in a daily basis? So the thing that they have in common, all of the problem that I just mentioned above, is optimizations. They're all trying to either minimize some things or optimize some things, or maximize some things, right? So for example, if we're talking about the cost of transportation, the cost of logistics, we want to minimize it. But we're talking about profit, obviously we want to maximize it, right? So things like that called optimization in problems in nature. All of these were created or was pursued to chase the dollar sign. Means what? Means we want to save money. If the company don't save money or don't make money, there's no point of the company being exist. They're designed based on mathematical modeling techniques. So what is modeling then? So when I think about modeling, as much as it's the math, it's an art. Means what? Means it's an open design problem. You can model something that has no exact answers. In the world of what we've learned mathematics in very beginning of the year, of our college year, we learned 1 + 1 is 2. Now 2 is the only answers. But in industry, 1 + 1 is not always 2. You know why? Because what is the chance of 1 being 1? Okay? So if 1 being 1, then 1 + 1 is 2. But what if 1 is not being 1, right? So then, there you go. You have probabilities. That's where statistics came from, right? Then you have to have confidence interval. You have to have things of that nature. Million and million of dollars of decisions is made based on statistics, right? Based on risk management. So mathematical models is a compact presentation, usually through the use of formulas, graphics, computer system, of a subject matters, usually through a set of data, okay, collections of events, layout, based on the model builder analysis and the knowledge of the subject matters, usually mathematically, statistically, and engineering. We'll be concerning about industrial modeling technique through deterministic environment in this seminar. Deterministic means 1 + 1 is 2. So what is not deterministic then? Stochastics, right? Stochastic means you employ the techniques of probabilities and things of that nature to come up with your decision making, right? So modeling in deterministic environments. Modeling could be used in about every aspect, not in just engineering. Maybe it's, a prospect of your life, right? The function of your past experience is who you are right now. Can you model your happiness index? Obviously. How much you can that you are happy depends on the interaction time with your family members. Maybe how many red lights that you go through to work. Maybe did your boss call you at 5 a.m. in the morning? I can collect all of those data, quantify it, and give you your happiness index. So mathematical models can be applied to about everything, not just math. We don't want to limit ourselves and limit our vision to just in the world of mathematics. We can apply mathematical models in just about everything, right? So there's two kinds of models. Models that have one exact answers and models that have more than one answers, okay? Today, I'm gonna go over both of them. So everybody remember these questions? Maybe from first time we've seen it from 107. We try to maximize a function. A function 2x1 plus 5x2. Subject to means a constraint. So an idea maybe in engineering, it means the resource amount that we have, how much money that we have, how much capital index that we have, things like that. In this case, we want to stay at the mathematical world. So subject to x1 plus x2 less than 3, 2x1, and all of that, you guys can read, right? So the method that we did, I think in 107, if I'm not wrong, Mr. Dush, or 110 maybe, is graphical. Means what? Means we draw a graph. We draw a graph, we look at a couple of the points in the graph. We draw a couple of the lines. And we say, OK, x1 plus x2 less than 3, so that we have that region. Then we limit in another region. Since all of the x has to be positive, which means the non-negativities conditions, we have the feasible regions with all of the points in there. Now, next steps, obviously, plug in those numbers back in the z and try to find what's the values of x. Now, everybody in this room know how to do it, so we don't need to waste time on it. By the way, those red dot points right there is a corner point feasible solutions. There's a mathematics lemma that going into x to y. Those points at the corners is the only points of a feasible solution, and not the points in between the feasible region. Okay? But because of the time, I don't have enough time to go over that lemma. So those are the components in the linear programming model that we usually have. Basic variables usually go through by the number of constraints. So if you look at the number of constraints right there, there's 2 of them. Obviously, there's 4 if we count xi is larger than 0. Means that x1 is larger than 0, x2 larger than 0. But those 2 constraints is not considered functional, means that it does not give you any extra information other than the non-negativity conditions. The other first 2 is called functional because it gives you extra information on it. Obviously, we have the objective function z. The non-basic variables is the total numbers of variables minus the number of constraints. So we talk about it when it gets to the next line, right? We got slack and surplus. Those are the ones that added to the original inequalities. If you look at the constraint, we have inequalities there. To obtain the augmented form means that we have to obtain the equals form, something that we have that we can solve. If we have less than or equals, we solve a region. If we have equal sign, we solve a line, right? Basic feasible solution is obtained per iteration. So Simplex method is going through different iterations in order to get to the final answers. In every iterations, the ith entering basic variables is replaced by a previous basic variable. So it means that there's an entering basic variables that enter the basic, and there's a one that's leaving out the basic. It will make more sense in the next slides. But this is an image of what iteration looks like. We got basic variables on the left. We got basics variable, non-basic variable coefficient at this iteration on the top. We have the right-hand side, and we have the ratio. So if we look at the objective function here, I want to transfer that into a standard form conversion because just out of intuition, we want something that has an equal sign to solve. Generally, it's easier to solve, right? So we have that equal sign. And that's exactly the motivations of having a slack variable. So remember, we have x1 plus x2 smaller than 3. So then we're adding x3 in there with the conditions of x3 being a positive number to obtain the equality condition. So we're doing the same thing for the second condition, and we keep the third one as being a non-functional constraint. So then we will obtain a standard form in Simplex. And notice that the introduction of the slack and surplus, sometimes the standard form is called the augmented form. Means that you have an introduction of a slack or and or surplus. So A, B, C, and D. So A is a matrix that containing all of the functional constraints. C, obviously just a coefficient. C is also a coefficient matrix that containing only those coefficients on the equation 0. D is what we try to optimize. And B is the right-hand side, which is 3, 4, and so on and so forth. So if we have 5 equations or so, we will have 5B, essentially. So that's explain that, right? And Simplex really just based on, it is the formal Gaussian elimination process that using, you guys all know Gaussian elimination, right? Am I correct? Okay. So standard form conversion, that's what we have in the previous slide. Tableau form. Okay, so here's what a tableau in a iteration looks like, right? So we have basic variables z, x3, and x4, equation number 0, 1, and 2, we have a coefficient of z, x1, x2, x3, and x4. The matrix right here is a coefficient matrix. Obviously, the top right here, c and d, representing the coefficient of equation 0. So z corresponding to z is 1, -2, -5. We don't have x3 and x4 in your first equation, so your right-hand side is due at 0. Your x3 is your surplus in the first equation. You have x1 to be 1, 1, 1, because it's a coefficient, right? x1, 1, 1 there. And then you don't have x4 in the second equation, then your right-hand side is 3, right? Same thing for x4, for your second equation. Same thing for the coefficient. Okay, so the next step that Simplex do is Simplex is going to say, okay, now I start at 0, 0 as my origin. Okay, that's this right here. Okay, so I have two options here. I either can move to x1 direction, I can move to x2 directions. Okay, in an economical standpoint, I'm going to move to the directions because keep in mind that we want to maximize z. So I wanted to move to the directions that I'll make more money. Okay, in x1 directions, I'll make $2. In x2 direction, however, I can make 5 per unit of incremental. So it makes sense for me to move to x2 direction than x1. So that's why x2 becomes your pivot column. Okay. So the next step, you have to figure out what is my pivot row. Okay. And the way that we do it is we take the right-hand side coefficient, which is in this case 3, divided by the pivot number candidates that I have, in this case, is 1. I do the same thing for 4. That also happened to be 1. So come up with the ratio 3 divided by 1 and 4 divided by 1. I'm going to choose the smallest positive numbers of that row to become my pivot row. Now, the reason why to choose the smallest one but not the biggest one is because we have to go back to these pictures. We're going to move to the directions, but there's 2 points in x2 directions that we can potentially move. That red dot right there and the dot be higher than that red dot. Now, the dot that higher than, the point that higher than that red dot on x2 directions is out of our feasible solution, which means that x4 right there. So we're going to move to the point where one of those slack variables become a 0 first. So in other words, if we move to x4, x4 will become a 0, but x3, but then x4 will be out of the feasible solution. So that's why we have to choose the smallest positive ratio. So now that I have a pivot number at 1, what I do next is I'm going to be doing a Gaussian elimination process in the Tableau method, of course. So what I do is I'm going to have to, now one thing that you have to keep in mind that pretty interesting is the basic variables here always has the norm of 1. Means what? Means the coefficient here that corresponding to this column right here is always 1. Everything else will be 0. Same thing for x3 and x4. 0, 1, 0, and 0, 0, 1. So that is the indication of all of these variables to be basic. What it means to be a non-basic variable means that you have something else. You have the norm of a different than 1, right? So now that we know that x2 has to move into the basic region, we know that x3 has to leave, right? So the next iteration that we're going to do is we're going to have to make x2 become basic variables, which means that in the column and in the row that corresponding to it, I'm going to have a 1 right here. Everything else will be a 0. That's what it means to be a norm of 1, or that's what it means to be a basic variables. Now, with Gaussian elimination process, because I see -5 here, I'm going to times 5 on these numbers. Times 5 the whole thing cross. So 0 times 5 is 0, plus 1 is 1. 0 times 5 is 5, plus 2 is 3, and so on and so forth. I'll do the same thing for my second equation. So that's 1, 1. So I would time -1 to here. I got 0, -1, that's 1, and so on and so forth. On the right-hand side, notice that this number changed. Okay, so what it means to be a simplex method is every time that you move to a different iterations, this number change. And that's how much you can gain. Think about it. X2, we can read off from this tableau to be 3. How much money per product in X2 that we can gain? $5 on the first equation. So when you move X3, 3 units, how much you can gain? 15, right? So intuitively, you can do it with the graphical method. This just be a non-graphical presentations of what you're doing. So, but the limit of the graphical method is if you have more than 2 variables, means that you have more than x1 and x2, this method doesn't work anymore because you cannot graph. How can you graph something that have the objective function of a dimensional bigger than 3, right? You cannot do it. So graphical method become obsolete at that point. Simplex is where you're going to have to employ that method in. So I already explained that to determine slack. Okay. So is really linear programming that easy? Answer is no. Because some other scenarios, what if we have a type for living basic variables? Means that what if the ratio is the same? You don't know which direction you're going to move. What if you have a type? It's called degeneracy. Means that per iterations, you're supposed to move from one point to another. Now, from one iteration to the next, you're just jumping basically on the same point, and you're stuck. That's called degeneration. No living basic variables means that usually you're going to have a positive ratios to be even qualified for basic, non-basics. Now, if you have a negative ratio, if you have a 0, then also it's an indication of an unbounded. Means that your z can be as much as you want or as small as you want. That's the unbounded problems. Or you can have a multiple optimal solutions, mean that you have more than one solutions that give you the max number of z, right? So there's things like that that factor into it. But the point that I want to point out today is simplex is what we use a lot in the world of industrial engineering because we're dealing with a lot of resource minimization, but we try to make the most out of it, right? We try to make the most money out of what we have limited. So that's why it's an important portion of what industrial engineering can do. So do I just do linear programming for a living? Answer, yeah. But not only that, we do more than just LP, right? So please take a moment, 30 seconds to also to go over this problem that I have on the presentation. So let's consider this. We got an OEM automobile supplier, tier 1, that has 4 manufacturing facilities. That's called A, B, C, and D here in Michigan. There are 3 main customers in that company. They're currently supplying goods for E, F, and G. Those are my customers. In 2014 of December, a company received a coding phase business, or an RFQ, means a request for code. For customer K, means that there's a new customer that coming into our door and asking for, can we do our job, right? Can we make this product to us, right? That SOP in 2017. SOP means start of production. The other 3 are currently in production and will phase out in production in the different MSP timeline, means a master scheduling planning timeline, right? A matrix of costs distributed from each facility to its customer is given in the next slide. Customer K wants to finalize the deal, location-based mostly, to move forward with the PPAP phase. So as an industrial engineer, please determine which location should be the best for the company situation. Means that how many products should I make in location A, how many products should I make in B, C, D, and D in order to minimize the cost, right? So I know that Mr. Lee is very interested in the world of graph theory, so I decided to throw this into the presentation, okay? So the cost matrix is given. I got on my column A, B, C, D is our facilities. On my rows, E, F, G, K is my customers, right? And the cost from A, manufacturing at A and move to E is 16 in thousands of dollars per unit logistics. Mean that in 16 numbers where there's really $16,000 to move whatever that we make from A to E. So all of that, so from B to G would be 18 and all of that stuff, then you become a matrix. Then you got on the far most right-hand side is your capacity. Means that facility A cannot make more than 40,000 units per unit time, and so on and so forth. And down here, I got the demand for customer E, F, G, and the customer K that I wanted to figure out where I should allocate my products at, right? So down here is one of the initial feasible solutions that I'm gonna have obtained from the cost and the capacity and the demand that I have. So, you know, does that really optimize? Means that is that the best mix of the products that I can make? No, but does that work? Is that qualify as one of my solution? Yes, that's why it's called initial feasible, right? Initial means it works initially, but is that the best? Might not, we don't know, right? Then total cost came out to be $1.5 million, $1,500,000, right? So on the right-hand side, here comes my favorite parts that mutually share with Mr. Lee and Mr. Dush here. So graphical, can we represent that information? I'm thinking, yes. Transportations, you gotta have a bunch of facilities and you have a bunch of customers. So customers don't ship the goods within the customers. Just doesn't make sense. How can you ship the goods from, if you're doing the same stuff, it's like, you know, illegal. Facilities, assuming that you don't have a transshipment node, means that you don't have a warehouse, means that you don't ship into an immediate location and then ship out from there. Means that if I make the goods at facility A, I ship it directly to customer F. So here comes my graph, right? So A to E, A to F, G, K, and so on and so forth. B is the same thing, C is the same thing, D is the same thing. In graph theory, this graph called a bipartite graph. Bipartite means that I can partition a set of nodes in my graph into two different sets where each individual set of nodes makes up my set of the G, of graph G, whereas there's no interaction between those individual sets of graph in G1 and G2. Now, the edge of GI has to be 0. The reason why is I don't have the shipment between my A and B or my A to C and so on and so forth, means that I don't have the transshipment cost or transshipment nodes. IJ is belong to EG if and only if I is in V1, V of G1, and J is in V of G2. Means that I just want to emphasize the fact that there's no H's in between G1 and there's no H's in between G2, and the interaction just happened between set 1 and set 2. Again, that's called a bipartite graph. Now, so how is that related into linear programming? So this is where mathematical modeling came into place, right? We have an objective function, which means we try to minimize, maximize, whatever, and we have a certain constraints, which means that I cannot exceed the capacities. At the same time, I have to satisfy my customer demands. So if we look at this objective function, we have cost, manufacturing at facility I, and move to the customer J, times with how much, which is a quantity of facility A to customer I. All of that stuff is being minimized, right? We try to minimize it. We try to minimize the logistics cost, total cost. In this case, we will have 16 of the cost and 16 of the the Q, just because the size of our matrix is a 4 by 4, right? Down here is a constraint, means that whatever I do, my quantity down here at A cannot exceed 40. Means that X A E, X A F, X A G, and X A K has to be less than or equals to 40, and so on and so forth. Again, now that is the row conditions. We obviously have the column conditions where quantity of the same customer has to add up to or less than or equals to 30. Means XAE, XBE, XCE, and XDE has to be less than or equals to 30. Now, you see, in the industrial engineer world, the size of the problem quite large. It's not about that pilot problem that we just did that just have two variables and you have two constraints. Dr. Nels probably knows very well about it. In industrial engineer, we probably have tens of thousands of variables and 20 to 30,000 of constraints that we have to deal with every day. So Simplex method seems to be by hand. Simplex method by hand seems to be obsolete because you cannot do that by hand. How long is it going to take you to do a 10,000 by 20,000 row tableau, right? That's just impossible to do. So it obviously in industry we have a lot of software that build executively to solve LP problems, such as Lingo, GreenQSB. Excel can do a little bit, but not much. Okay, and I don't have enough time to show you guys that. So I'm just here to introduce a couple of the options when you actually solve industrial problems. So look at this, right? Flight scheduling, aviation traffic control. There's about, during the peak travel times, it can be 5,000 aircraft over American at once. Think about it. How can they schedule that? Because each commercial flight is restricted to fly less than a certain altitude, right? So how do they schedule that? How can we, doesn't heard of any plane crash or anything like that on a daily basis? LP, linear programming. You try to maximize the traffic control with all of the constraints that you have. Linear programming is the key, right? So just to wrap up for LP, always keep in mind those things. Later, as an industrial engineers or engineers in general, always keep in mind that humans' involvement, regardless of technology advancement, that's why you need a person who can model an objective function, a person who can understand a constraint, a person who can put that into the computer and let it solve. It always needs that. That's why we're here. That's why we get educated, right? If the computer can solve everything, then what's the point of going to school? I can just be a friend of my computer and not having my bachelor degree, right? So it's always need us to do that. What is that you try to optimize? To be really accurate, to be really concise. What are you trying to do, right? What is your constraints? What is that prevent you from moving backward? I don't know, that's probably because the mouse. Okay. What is that prevents you from optimizations? You gotta know your constraints, right? And last but not least, human can just do so much, right? If you cannot figure out the answer in one day or 1 week or 1 month, okay, try again. Don't feel bad. Engineer has a bad day, okay? Just like mathematician, we have bad days, all right? And this is my favorite quote. I woke up this morning and realized that I don't have what it takes to sit back and be an average people, okay? So, again, go back to our formulas that we have at the beginning. Career as an engineer is applied math and politics, which I don't want to talk about. Applied math It's not only OR, but it's also statistics. So why do we have to be good at statistics? What does the central limit theorem does? What is confidence interval? What is chi-square test, F-test, T-student test, 95% confidence, all of that stuff? Why do we have to be good at statistics, right? That's what I want to talk about. Let's consider this problem. You are a new hire industrial engineer to an engineering consultant firm. One of your first tasks is to impress your boss of your intellectual vision of the small size sedan market. Based on the past data, predict the sales of the next 24 months in the economic market. Impress your boss. That's what it says. Okay, so go ahead, go online, look at the past data. This is the sales in our past 5 years. Can you predict what we sell next month? Can you predict what we sell next year? Because sometimes it goes back into our capacities, right? We can just do so much in our manufacturing facility. At some point, we ran out of capacity. We have to buy a new machine. We have to buy a new facility. We have to hire new engineers. We have to do this. We have to do that, right? This forecasting is very important for engineers, especially industrial engineers. So forecasting techniques is really a math model. So you're trying to create a model that can forecast future data. So here's a couple of the techniques that we currently use: regressions, exponential smoothing, first and second, with and without seasonality, adaptive rate, and etc. At this point, I want to show you guys what is one of the assignments that I'm currently working on for my senior design project. So if we look at the data, this is the data of the sales from the last 5 years. So the white is the domestic auto sales in the US. And all of the X's is what I think is the dependent on the Y, right? It also has a number in there. And it's go through similar linear regressions that calculating the seasonal index, how you de-seasonize it, and then you run a statistical test on it. And then you have a coefficient of A, coefficient of B. Obviously, you have Y equals B plus AX and things like that. And see how much you are confident at your result that it would be the case through F statistical test, a variance test, and you have your R square is your coefficient of correlations, and you have all of that stuff, right? And you have your F and you have your p-values. If your p-value is less than 5%, providing that you're testing in the condition of 95% confidence interval, if your p is so less than your 0.05, means that you fail to reject you reject the initial hypothesis, which means that you don't have a correlation of B or of A, and things like that. And then moving average, and so on and so forth. I just wanted to show you guys how big of a data analysis that you guys will be expecting to do. I mean, right? How big of a data analysis that you're expecting to do as an engineer, right? Exponential smoothing, multiple regressions, means that I'm going to run a regressions for Y with all of the Xi's to be my independence variables and come up with a formula for it, right? So same thing for a single simple linear regression. I'll come up with some intercepts and some coefficient that corresponding to it. So this would mean that my Y will be equal to negative 67304 minus 1298 times X times T1 plus 0.67 times X2 and so on and so forth. So, and obviously down here is your plot against each of the individuals, and then the way that you can test for the goodness of your data is through MSE, mean sum of square, right? So if you try to minimize your MSE so that you can accommodate all of the data in the past and then use that model to predict what's going to be happening in your future, right? So I just wanted to show you guys what really is that an industrial engineer is up to, right? So again, go back to the original questions. What does it mean to be an engineer? and when are you becoming ones, right? Am I saying that we have to be Einstein? No. Am I saying that we have to be Donald Trump? No. Am I saying that we have to be a good politician in order to become a successful engineer? Neither. But if you have what it takes, if you have a combinations of these, this is the key, right? This is what you as an engineer is going to be up to in the future. Realities. If you're not good at politics, means that if you're not good with communication with other people, you doing good, your good job, you come up with the models, right? You Einstein, you come up with the models. You run regressions on 6 years worth of data. You come up with the mean square of 200,000. The other guys come up with the mean square of 3 million. So yours better. But the other guy has a better communication. What can you do? At the end of the day, you're still going to be an engineer. He's COO, Chief Operation Officers. And the guy who come up with an MSE of 2 million is a COO, and you come up with 200,000, you are still an engineer. Think about it, right? Politics. It doesn't matter how good you are mathematically. Well, it does. I'm sorry. It does. But
just remember where you are right now.
Exactly. Just remember who you are. And as an industrial engineer, I do believe that every day, everything that we do is that. Chasing the dollars. Chasing the dollars. How can you save costs? How can you do something with less cost, more productivities? That's the only thing that you do really, as everything. Think about if you sit out in the conference with your president and you teach him a new product that you just designed as a mechanical engineer. Okay, this product is great. This product is unique. Okay, I'll tell you this. If you make this product, nobody else in the market is doing it right now. You know what the president is going to get up at you? Can I make any money on that? Now that's where the other kind of engineers fail to answer because they don't know this. They don't notice this. Business exists because of money. Okay? That's the end of the story. If you don't make money, how can you pay the salary for your employees? How can you proceed into a top 5 OEM automobile supplier if you don't have the money, right? Mechanical engineers, great. Electrical engineers, great. But if you have a knowledge of money, that's where you're being set apart from different engineers. And that's why industrial engineers usually become heads of the company, because when you sit down in a room that has a group of engineers and a group of people who just know about money, so marketing, financing, president, COO, all of them cares about money. We cares about the integrity of the products. Industrial engineers is the only person in the room that know both. Think about it, right? They are the only person in the room know both. When you talk about engineers, okay, great, we do it, no, too, but president don't, right? President cares about this, and vice versa. So please, I'm telling you right now, this is what you're gonna do in the future. This is the real realities right here in front of you. If you don't like it, if you don't like the data Excel sheet that I just showed you, it's saying it's too much of a work, by all means, get out right now. Do something else. If you are good at playing pianos and you think that you will become the best piano players in the world, by all means, do it. Even if you are in this last semester of being an industrial engineer and you realize, oh, I'm good at playing guitar, do it. Get out. Because what's the point of being in the career for the next 40 years if you are not motivated to go to work, right? Think about it, 40 hours a week, maybe 45, maybe 50 extra, 50 hours a week times 40 years. how many hours you're gonna waste on something that you don't love? What's your happiness index? Can you model it? So here's my, for students, here my contact information. If, because I'm working in the engineering planning department, I do accept a lot, I do think that because of the fact that I came from here, I really wanted to help you guys to become a better, in a better positions. So if you have resumes, questions, concern, email me as a source of, as a good resource, you know, for you to ask, okay, if you know, if I were gonna do this, you think, you know, you have 5 minutes to have that conversation. I'll do my best to, in the limit of my knowledge, to do so. So if you have any questions or resume that you want to send out, Denso is the second largest automobile supplier in the world. And their headquarters is in Battle Creek. So if you happen to transfer to Western or anything else, it's a matter of fact, because in summer you're usually going to have a summer co-op, right, as an engineer. So if you do so, if you really wanted to pursue a career as an engineer and you want to work for Denso, please do some homework and send some emails. All right? That's the end of my presentation today. If you have any questions, let me know.